Okay, organic chemistry 2341. We're going to continue on with chapter 11. We're going to looked at making alcohols even better leaving groups than before, just like with the thionyl chloride, and also protecting those alcohols. Let's say we wanted our alcohol in our final product, but we had problems because the alcohol would have reacted otherwise. So let's look at those two different systems in our this video here. So the first thing I want to do is let's go ahead and make an alcohol a better leaving group. Remember, hydroxide is a poor leaving group, and by using something to make it a better leaving group, we can then react it with a wider number of nucleophiles. So the one I want to talk about today is called an alkyl tosylate. So tosic acid is a toluene sulfonic acid. It's also called the tosyl group. And what we do with that is we use it to react with alcohols to create this tosylate ester. And when we say tosylate ester, this right here is the sulfur analogous to an ester right here, and it becomes the leaving group so that when a nucleophile comes and reacts with the carbon over here, it actually leaves completely with the system, okay? So that creates this tosic acid as a leaving group. Notice that that anion would be delocalized over 3 different atoms, and therefore it makes it a really good leaving group. Okay, so let's look at that in a little more detail here. So to form this, what we would do is we'd take the chloro version of this sulfonyl tosyl chloride, or it's toluene sulfonyl chloride or tosyl chloride here. And we're going to react it with that alcohol in the presence of a base. The reason we need the base is that we're going to generate HCl, and we need to be able to remove that HCl to make sure the reaction gets driven to completion. So we take any alcohol here, like a primary alcohol, for example. Again, that hydroxide makes it a very poor leaving group. We react it with the tosyl chloride to giving us this sulfonate ester group here. And our HCl is taken up with the pyridine right here. Now, once we have that on there, that means that we can displace it with any really good nucleophile. And the whole point about making this a really good leaving group is the fact that this tosic acid here is very strong acid, and therefore it makes this anion, it can delocalize over all of these oxygens, making it an even better leaving group with that resonance system. Okay, so because that tosyl group is such a good leaving group, we can undergo with even mild nucleophiles. Okay, now if we have a weak nucleophile or a good nucleophile that isn't a base, what we're going to end up with is we're going to do an SN2 reaction and we get substitution. For example, in this case here, we're using the alkoxide as a strong nucleophile. It's a good base too, but it's small enough to be a good nucleophile, and therefore we go through SN2 substitution. However, if we use a big bulky base, so it's a non-nucleophile, but it's a base, we can get that E2 reaction, meaning the proton from the carbon adjacent to the one with the tosyl group is going to be pulled off. Then those electrons are going to kick in, and we're going to kick out our tosylate group and get our alkene derivative. So this is a good way of taking an alcohol, and we can specifically use that one alcohol to remove it to create an ether in the case of our nucleophilic substitution, or an alkene in the case of our E2 elimination. Okay, so tosyl group is not the only one that can do that. The tosyl group is highlighted here. It's this toluene sulfonic acid here, but there are several different derivatives. All of them include the sulfur having 2 double bonded oxygen to it and some kind of alkyl group. So in this case here, if we had a methyl group here, that's called the mesyl group. And so it's just a methyl group. It's not as acidic as the tosyl group, so it's not as good a lead group, but it's still a lead. Here we have an electron withdrawing group, a trifluoromethyl group here. This is called the trifluoryl group. And these are very reactive species here and are very easy to remove because they make very good leaving groups. Because of the electron donation, the electron withdrawing group here makes it very acidic and makes it a much better leaving group, even the tosyl group here. So we have the tosyl group It makes alcohols better leaving groups, and we have two derivatives, the methyl and the trifluoromethyl, which is the mesyl and the trifle group. So we're using these sulfonyl esters to make them better leaving groups, more susceptible to E2 elimination and SN2 substitution. Let's say we wanted to actually protect the alcohol such that we wanted the alcohol in our final product, but that acidic proton, that hydrogen bonding proton, made it impossible to do the reaction we wanted to do. So what we do for that is we call what's protecting the group by blocking it to reactions and then regenerating it at the end of the reaction. So in this case here, we have a primary alcohol, and it will react in our species with acids or bases. It'll react and not allow Grignard reactions to happen. So we have to protect it in a group that doesn't react with these species. In this case here, we're going to use this isobutylene group right here and HCl. And what that's going to do is that's going to generate a tert-butyl group as an ether here. Notice that we're going to have the electrons from the oxygen kick in here to generate that, and then the hydrogen is going to end up on this terminal group, giving us our T-butyl group, okay? Don't worry about the mechanism. It's just the idea that we're now making an ether. Remember, ethers have very low reactivity, so we can use that as a protecting group to be able to generate lots of different things, okay? So when would we use this, okay? One good example here is, let's say we had this compound right here, this bromopropanol, okay? And we wanted to react it with a good nucleophile here to displace the bromide and extend the carbon chain, okay? If we took that acetylide salt and added it to there, it would react with the proton of the alcohol to deprotonate it, and the reaction would quench and we'd liberate acetylene, okay? So that's not the reaction we wanted to happen. So instead, what we would do is we would take the sulfuric acid and the isobutylene, and that would protect it as the T-butyl ether. The T-butyl ether is not susceptible to acid and base chemistry in this case, and therefore our acetylide ion will act as a nucleophile and displace our bromide, generating our new material here, 1, 2, 3, 4, 5, which is be our propyne, okay? And then just by adding acid, it'll undo and create T-butyl alcohol and generate our primary alcohol plus our T-butyl alcohol here. So we'll end up with our propyneol. So again, we use that T-butyl group to protect that alcohol because we wanted it in our final product, but the reactions would not let us do it because of the acidity of the alcohol. So there's also another really common protecting group we use for alcohols, and it is the silane group, or the R3S group. The great thing about the silane group is there can be a wide variety of ones. It could be trimethyl, it can be this one right here, which is the butyl dimethylsilane right here, which is called the TDS group. And we typically react it with the chloride here, just as we would with the thionyl chloride or the tosyl chloride. Then we want to use imidazole as a base. Any base will do, but imidazole is used commonly in this system here. And what it does is it turns our alcohol into a silyl ether, okay? This silyl ether is very non-reactive to a lot of different nucleophilic substitution reactions, okay? So you can do lots of acid and base reactions. It's the silyl ether reactions, but the cool thing about the silyl ether is it's very susceptible to fluoride ion. In fact, that's the #1 way to break it up, is to add any kind of fluoride ion to the system. It then displaces the silyl ether, creating that silyl fluorine group right here, and you regenerate your alcohol. So we can use the isobutylene group to protect the ether. In the cases of strong acids and bases, we can use this trimethyl silyl group anytime we're not using fluoride ion.